All right, let's talk about the parameterization of x equals cosine t, y equals sine t, t going from 0 to pi. Now this is not going to be a line segment like what we just looked at because of these cosines and sines. In fact, if you recall from trigonometry, the point cosine theta comma sine theta is the point on the unit circle corresponding to the angle theta. So here's the thing, t, as we see up here, can be thought of simultaneously as time and as the angle theta. We've been thinking of t in parameterization as being time, but what if this same t, let's just also say that it's t when it's convenient. Let's think of this t as just being a theta to kind of remind us of the angle from trigonometry when it's convenient to think of it that way. Because if this is now both the time and the angle, then think about what happens when for a certain moment in time, maybe your t is equal to pi over 2, so that'd be the sorry, I shouldn't even say 90 degrees yet, but pi over 2 is t, and then that's not only time, but it's also theta. So pi over 2 is the angle, meaning that's the 90-degree angle if we convert from radians to degrees, and we're trying to get the point on the unit circle then, right? So cosine of that angle pi over 2, sine of that angle pi over 2, give you the x and the y coordinate respectively, and you actually end up getting a point on the unit circle this way because cosine theta sine theta is cosine t sine t. Right now, if theta is the same as t, well, you get the same thing. You get a point on the circle. The thing is here, we don't get the entire circle because we only looked at t values from 0 to pi. So yeah, you could view t as being time, but when it's convenient, t could also be an angle. It's just our convenience of interpreting t as being an angle because t happens to be used as an input to a cosine and a sine. If we want more of the circle, of course, we could make that happen by changing the values of t. We show this arrow in the sketch. You know, this is showing the direction of parameterization. It, in a sense, shows the direction that a bug travels. So you draw the arrow leading away from points with smaller t value and leading towards points with larger t value. So this bit of arrow here is trying to suggest that the bug would start right here and then traveling along this way counterclockwise, ends up right over here, right? So if you wanted the bug to travel in the opposite direction, there's ways to take care of that. You'd have to write the formulas for x and y, or at least one of them, a little differently. We won't get into that quite yet. I'm just trying to point out, I'm saying too much right now. The arrow represents what direction the bug moves, right? So it's like a one-way street, and the arrow indicates which direction the bug is traveling. So let's take a look at the parameterization x equals negative cosine t, y equals sine t, 0 less than or equal to t less than or equal to pi. So instead of x equals cosine of t like we saw earlier, now we have x equals negative cosine of t. Well, look, if the x coordinate we had a moment ago is swapped for the negative of what we had, right? We used to have cosine of t. Now we have negative what we used to have. And we've only swapped the x coordinate. So the y values, just in the previous picture, please recall they were above the x-axis because all the y values were bigger than 0 or bigger than or equal to 0, and that has remained the same. The y values are still positive, so if we just flip each x coordinate for what its negative was, this is sort of like the like graph transformations. It's the parameterization version of transformations if each old x value is swapped for the negative of what it used to be. Okay, so again, the arrow shows the direction of parameterization. Really, yes, this really works. Think about it. Go ahead and actually substitute 0 for t. And then you'll have x coordinate up here is x is equal to negative cosine of 0. And the cosine of 0 part simplifies to 1, right? So the minus sign we still have to draw for and account. So x equals negative 1 and y will still be 0. So you start at the point negative 1 comma 0. This point that is right over here, kind of to the left of the origin. So this arrow indicating the direction of parameterization here is correct. Okay, so I think I already said this in sort of a preview sense, but if you compare x equals f of t and y equals g of t, let's say you start with that, to a new parameterization, x equals negative f of t and y equals g of t, that's a transformation. In this case, it's specifically a horizontal flip. So let's talk about sketching the parameterization x equals cosine t, y equals sine t. So the x and y formulas are back to what they used to be. But now look, the t values, we're looking at a bigger collection of t values. So it's not 0 to pi, now we have 1.5 pi. So we have more, right? So this goes up to the angle 3 pi over 2, which is the 270 degree angle. So here's your interactive question for the day. How would the formulas for x and y look, and what would be the starting and ending t values in order to obtain just the portion of the unit circle in the second quadrant? All right, let's look at this. Sketch the parameterization x equals 5 cosine t and y equals 2 times sine of t from t starting at pi and ending at 2 pi. Oh, here's lots of things going on different. So let's ignore the 5 and the 2 for a moment. And if we just pretend the 5 and the 2 aren't here, we'd still have unit circle, right? X equals cosine t, y equals sine t. It's just the angles from pi to 2 pi. Well, that would be the bottom half of the unit circle. But then let's think about what the 5 does. I mean, what should the 5 do? Again, the x value used to be just plain old cosine of t. But what happens when you multiply that each old x value of cosine of t by a 5? Then everything stretches out by a factor of 5. Well, everything does, but I mean every x coordinate should be 5 times as large. The y coordinates stretch out by a factor of just 2. So we have this bottom part of the circle. Let's see if we stretch horizontally by a factor of 5 and stretch vertically by a factor of 2. Here's a picture. Let's just give it a second to load. What we're actually seeing is the bottom half of the unit circle, still oriented. This app, I can't get it to draw the arrow, but at least you see the animation of that red point. So you can kind of see that counterclockwise-ness. But it's not just the unit circle. If it were, it would have just been located right around here, right? But instead, that unit circle, or rather the bottom half of the unit circle, has been stretched out by a factor of 5 horizontally and stretched out by a factor of 2 vertically. So it's actually the bottom half of an ellipse. Okay, again here, the arrow in the app that I made doesn't show. I just don't know how to do that, but at least you can see the movement because of that point that's shown in red. Even though the interactive question of the day is done, I think I would challenge you to try the following. Modify the example above. You can even change the values in the app. But before you do too much else, just try making a change. Like, let's say you change the 5 here to a 7, and you'll notice it hasn't changed yet. I just need to now click the mouse away from this input box, and then the change will actually occur. But you should think to yourself, what will happen when you do this? And what happens if I stuck a minus sign in front of this so that I have y is equal to -2 sine of t? I mean, you can totally do this in the app. And what if I just change this, instead of from pi to 2 pi, 2 pi is approximately 6.28. It's not even quite perfect, but close enough. We can barely see at the end of this. But what if I just change this to 6.20? What should happen, right? You can go ahead and make some predictions and then just test it with this app. There's nothing you can break on this app, so please give it a try. Here are some suggestions for things to try. How about x equals 5 cosine t, y equals sine t, where you just remove the 2 from up here? What about if you put a minus sign in the y formula from what was originally up there? What if all you did was just you kept the x and y formulas, but you changed the t bounds? Just lots of options to try. Here's next slide, an example of 3D parameterization. So cosine t, sine t, that should still form a circle, but now in the new direction, in the z direction, t used to represent an angle, and you could still say it does, but it might be nice to say, hey, over here, t represented time and angle. Now, when looking at this t, we'll just pretend that t no longer represents an angle, that t only represents time, for instance. And so as time moves on, the time value is the same as what the z-coordinate needs to be. In other words, think of it like a bug is normally just traveling in a circle. If you look from above where the z-axis is, maybe a bug is just traveling in a circle, in the shape of a circle. And if you didn't have any depth perception, that's all you'd see, just traveling in a circle. But because of where you are located, maybe you don't actually see, if you're up here at the positive z-axis, you maybe don't even notice that the bug is headed towards you because it's increasing in height. So as t moves on, as t gets bigger, z gets bigger. So you see this sort of slinky-like shape right here. Okay, so I don't expect you to take a look at these next 2 slides, and I'm not expecting you to ever recreate things that look this wild. I just want you to explore and just see. So I'm going to click to show you Here's a parameterization that's in 3D because of an X formula, Y formula, and a Z formula. And I just want to show you what this looks like. You can actually go and modify this as well and you'll see in the left, you'll see X versus T and Y versus T and Z versus T in red and blue and black. And then you'll see that parametric curve or parameterization here in 3D space on the right half of this thing. And you can use your mouse to spin this around. And if you actually kind of fling this with your mouse, you can get this thing to move for you a little bit to get different perspective. And I'm actually changing the value of T. So this one looks, looks like it's kind of going up and down and up, and from the bird's eye view over here. So the blue one, I believe, is the Z-axis. I guess I don't know, it's a shape that's sort of boomerang-like or something like this, just to get some different views. What I did then is, here's another parameterization that looks similar, at least in the X and the Y formulas. Where earlier the Z formula was a cubic, now the Z formula is a quadratic, squashed by a factor of 20. I'll just see what that one looks like. It's just a little different. It's just different is all it is. So what's going on is with the Z formula, we'll see that in this picture, the point starts kind of up higher at the Z value of around 3.2 or something like that. And then the Z value falls, and then the Z value increases. Because after all, this is just T squared is a parabola, right? So you'll see, in fact, let's see, how should maybe I'll spin this around again. And let's just start T back over here at -8. And as I increase T just a little bit at a time, you'll see that the point you're getting, maybe this is too much movement. Well, let's stop the movement of this over here. As I increase the value of T, the point has oh, that's the dog over there, has smaller height and then has larger height. All right, let's go back here. So in each, please try out these apps, move the slider for the parameter T, look at how the red, black, and the blue curves, that is, over here, this, X of T, Y of T, Z of T, how does that relate to the purple curve on the right? Account for every number. What's a T value, what's a Y value, and so on. So for instance, like right here, take a look. Let me just try to pick something where it's visually possible to see it. Oh, see, there we, let's try that. -1.4 is T right now, right? Then look at 2.049, that's an X value. Let's go in order. Blue, let's see, so -2.9, that's a Y value, and then 0.09, that's a Z value. And for that one moment in time, so at the time -1.4, maybe -1.4 seconds before the experiment starts, or -1.4 seconds before midnight, the bug is located at this point that's drawn here. Its X coordinate, it's hard to see because of this sort of graying of the XY plane, but the X coordinate is 2 point something, and the Y coordinate is -2.9 something. And oh, I can move this around, cool. And the Z coordinate is 0.098.